Oh yeah, recording. Thanks. So maybe I can start like sharing about SSE. It won't take long. And then we can go right into updates after. So we can also like wait for more people to join. So let me share the screen, and it's actually probably like half my update too for last week. So I spent some time studying about SSE and SSE partials, as suggested by Justin Drake. And so, what is SSE? It's basically a serialization method. Imagine like you have some message to transfer over the network. Your data is in a different format, so you have to have some kind of like serialization so that you can communicate it over the network to other clients and other instances. That's where serialization is useful. Another part that serialization is important for the consensus layer is also for well, the consensus, because you need a way to kind of like share the view of the beacon state across with all the instances of the clients that are running in the network, right? So we use serialization in order to kind of like compress the state and then be able to hash it or Merkleize it so that you can send it across the network and be able to kind of compare it with each other that you are actually have the same full state as other clients in the network. But for example, yeah, so for example, I showed here, we have like this beacon block. Basically, this beacon block body has to be sent, uh, yeah, the block body has to be sent across the network. So you have to have some way of serialization that. Also, the beacon state. It's also important that all the clients in the consensus layer share the same view. So we basically serialize this and then Merkleize this in order to share the Merkle root with all other validators so that you can compare. And then if the Merkle root is the same, then you're basically having the same view of the network. There are actually two serialization methods in Ethereum. One is called the RLP, or recursive length prefix. This is from way back before even the merge or even before the beacon chain is up. So it's basically using the execution layer as well to encode things. Um, but for the consensus layer, we actually, um, well, the Ethereum developers came up with another serialization method, which is simpler and also kind of like more tailored towards consensus use. And that is called the simple serialize. Um, so basically, I would say like this serialization method is basically crafted for specifically the consensus layer. For example, like if you look at the types that are available, it's basically covering just enough for the consensus layer to work. So basically, you only have like the basic primitive types are only unsigned integer, byte, and Boolean. The rest are composite types, a container of other values, vector, list, bit vector, bitless, and unions. And this is basically all that the SSC is able to do. Um, I think another interesting thing about this serialization method is that it is schemaless. So you have to know the schema in advance. I think that's also important to know. I kind of like struggled with SSC decoding and coding at the beginning because I thought the schema is inside as well. So you actually need to know the schema upfront in order to be able to decode things. So that's also important to know. Another interesting thing about this is that SSC is made so that it's easy to Merkleize the entire structure as compared to RLP. RLP is not designed to be Merkleized, so it's only being very useful in terms of like serialization and then basically sign the serialized message. That's what the RLP is good at. But for SSC, what's more important is that it's also able to Merkleize. The way that I understand that it's able to do this is because there's like so little like number of types that are available, and then all these types and even composite types are basically divided into chunks. chunks of 32 bytes, and because of those chunks that are basically 32 bytes, you're able to Merkleize it, um, each of the chunk. And if you have like say 4 chunks, then you Merkleize like each of the 2 pairs, and then you Merkleize them again. So in the end, you are able to basically Merkleize all the data inside the simple serialize into a single Merkle root. Another interesting thing about simple serialize is that there's something called summaries and expansion. I think this is pretty cool. So basically, what this means is that if you have basically beacon block versus beacon block header, what is interesting about this is that for the beacon header, um, the beacon block header, you can see here that it has the slot, proposer index, the parent root, state root, and body root. What it's able to do is that if you are sending only the beacon block header, then you will only see these 3 roots and these 2 data. Interestingly, if you need the beacon.
Sorry for interrupting, but I think the screen is not changing. Yeah.
Yeah. So for example, the beacon block header, you have slot, proposer index, parent root, state root, body root, and this is basically just a root, right? Not the data inside it, right? And you're able to send the beacon block header pretty efficiently across because you're not actually sending the content of the parent, the state, or the body itself. You are only sending the root of it, right? But if you want to actually get the content of the body root, you're also able to get the body content, the body beacon block body, I believe. Yeah. So what happens is that you're also able to get the beacon block body. You can then Merkleize all this information back into a single beacon block body root, and then this block body root is supposed to, for example, like here, beacon block. You can see here that if you plug the entire beacon block body in here, you can actually compare the root of this beacon block body against the root that's actually stored here. And then you're basically able to kind of expand it into a fuller content based on the root that you can compare between the two data. So that's interesting thing about the SSC. And also quickly, I want to show you this. This is also a pretty interesting, pretty good tool to kind of like visualize how the SSC work and how it looks like behind the scene. So I'm not so sure it's made by Shainsef, and it's under this domain ssc.dev, so you can kind of like play around with it. Some example is, for example, index attestation. You can see here that the actual index attestation actually has three data here, attesting indices, data, and signature. And what it's able to do is that when you have a really large indices, you see that the data is actually just here at the bottom here. And then in order to actually serialize it under SSC, you have to Merkleize it by pair. And then once you get the Merkle root of each pair, and then you can keep Merkleizing back until you have only a single hash back on top of here. I think most of the SSC libraries are also built in a lot of helper functions in order to do this. For example, like if you have like a number of like data here, you can put it into a function that would calculate that. For example, like if you have 6 items to Merkleize, then you can put it into a function and then it's able to kind of calculate that how many fillers that you actually have to add on. For example, if you have only 6 items, in order to actually be able to Merkleize it, it has to be a power of 2. So it's able to kind of like know that, oh, then I have to append it with 2 more blank items. So it becomes 8. And then with 8, you're able to Merkleize it back to a single hash value. Why is this important for also like for the beam chain. So I guess like just to kind of like quickly summarize it, when you're working with the state inside a client, then you would be storing the slot and block roots and all the state um, parameters or data in the way in the programming languages that you write in, right? But in order to be able to communicate it across the network, you have to serialize it, and you have to serialize it with SSE. And in order to actually compare your kind of like state view with other validators that are running in the system, then you will need to merkleize that. And that's only kind of possible or easy to do because we are actually using SSC that's very convenient to merkleize back into a single like Merkle root. The interesting thing about SSC for the beam chain is that as I did, and also like Jun did when we did our kind of performance benchmark of the CKVM, we basically load the entire state into the CKVM and perform like functions, all the process functions, process operations in there. It turned out that it took really long time to load the state in there because the state for Ethereum, especially on mainnet, is really huge. And it's definitely not practical to load the state for each of the block into the CKVM and process it. Right. So the also another interesting thing is that, but if even though like we load the entire state into the CKVM and we don't keep track of the SSC or the serialization form of it or the Merkle tree, each time that, for example, like we add a new validator into the state, we would then have to um, re-encode the entire state and then also re-merkleize the entire tree, which is not ideal for to be done under the CKVM. And from that, my understanding is that Justin suggests that the way to go is that maybe we load the entire state at the beginning, for example, at the genesis or at the when with the CKVM is initialized. But we should also keep track of the SSC encoding and also the Merkle tree of the state. Because if we, for example, like each of these leaves should correspond to a data in here. For example, leaf one could be slot along with its tree there. Leaf two could be the block roots. And what happens is that if we are not updating the validators, the validators stay still, then we shouldn't have to touch anything about that. The interesting thing after that is that when we change one of the leaves, for example, like H3 here, the only thing that we need to compute is H1 and H0, right? There's no need to recompute H5, H2, or anything like that. So once the state grows, we should only touch the data that we really need to touch or change the states. And then we should be able to only recompute only the parts that affected in order to get the new state root. So getting back to this, I guess when we did the quick benchmark, this is what we got out. Right? And I think Jun also had a similar number from SP1. Is that reading the state, the pre-state is actually the most time consuming. For me, it's 92% of the cycle counts here. Reading block, not so much, and process block header is a bit more, but then also still kind of like tiny amount out of the entire thing. So with this, I suppose this is also not this is only just like state transition. It doesn't include SSC and merkleization that's going to be needed for each of the state. So with this, even with this, it's already taking a lot of time. Then in order to actually process process the state under the CKVM, then I think it's very important to be able to keep track of the SSC and the Merkle root and only update the parts that's necessary. From what I've seen so far, and also I think another interesting read that if anyone is interested, I think Lighthouse kind of like already moving towards this. So August 2024, only a few months ago, Lighthouse introduced 3 states. So basically, what they did is that instead of actually just like storing the data in the memory, whatever the um, the programming language kind of like figure it out, they are actually storing the beacon state in a hash tree. And more interestingly, for each of the state changes, they are actually not duplicating the entire state. What they do is they are only tracking the changes from from one slot to another. And for whatever that hasn't changes, it basically refers back to the previous beacon state that it has. And they also mentioned a few benefits, not only that it saves a lot of storage, but they're able to kind of like jump between states. For example, like if you need the finalized state, then it's basically one tree. And if you need like the most recent state, then it's another tree, right? So when they need to do any kind of like reorgs, they don't need to kind of like go back in time and try to recompute the state. They can basically go back into the state at whatever slot that they have to reorg and then build it from there. So yes, and so far, I guess like a small thing that I try to find in Rust is that I look into all the Rust libraries that do SSC. Obviously, like we have SSC libraries available for Rust, but I don't think any of them are able to do SSC partials. So basically, if you wanna um, if you wanna serialize the state, you basically have to kind of like input the entire thing in there, and then it will serialize and then localize the state for you, right? There is no library that's able to have like say, oh, I only want to change the slot. Please keep track of the rest of the serialization and the roots, and then recompile only the parts that's changed. I don't think any library is able to do that. The only one that I see uh, that might have this is Grandine. They have the SSC crate in there that I see that you're able to have like push a new leaf into the data structure, and then it's able to kind of like remorphalize it. But I haven't looked into like the specifics, so I'm not sure 100% if it's actually working like fully yet. And also, I think another thing is for Grandine, they actually put it as like internal crate within their like Grandine client repo. So I'm not so sure if that's actually a good idea if we want to kind of like reuse that, since it's not like a kind of like a published crate. So I think that's also something that's kind of like up for discussion as well, whether like implementing like SSC partials is a good idea to do. Yeah, so I that's I feel like that's what I kind of like took up to learn or study last week. Yeah, and I guess like open to any questions or any additions.
Awesome, Anand, thank you. Just a couple of questions. Is this just a representation, or do each of these leaves represent a particular? I mean, as you've described, one is a block number, the other is validators. Uh, I'm just keen to understand. I mean, as I was saying you in DM, which part is likely to change? And when you mention partials, is it a particular leaf alone that we would need to recompute the SSC as well as normalize it?
Yeah, so that's also a question that I'm trying to answer. I couldn't show it here because once I load the state, it basically would crash my browser tab because it's way too big. But I think one thing that I can refer to is the beacon state here. So so this is beacon chain, right? And I think we are expecting like a lot of these go away for the beam chain. But for example, like I think the slashings are probably not gonna change all the time. Like some of these stuff, like for example, slot is gonna change every slot, right?
Change, yeah.
Some other stuff, for example, random mixes. I think even though like we probably not have it in the beam chain, but then there are other stuff that are probably not gonna change slot by slot, Some of them are going to change per epoch, and there's no reason for us to recompute for every slot.
Yeah, the validators would definitely change for sure, but we don't know. I mean, how do you identify the validators? Because the entire keygen mechanism itself is going to change. So uh, I'm not sure how we identify it in the current state. Is it based on an address or validator address, or because that would change if we are using a different? I don't know. Maybe I'm not explaining it correctly. Did anyone understand what I'm trying to convey? If you're using a different signature scheme and you have to generate uh, several keys for Winternets, then how do you uniquely identify each validator? Would the format of the address change, or rather, this is more a question for Philip if he's still there. This was my question even when there was a presentation of Winternets. I don't know. I'm still not clear on that.
Maybe I can answer this question. So
Yeah.
I guess Winternets is an oversimplification of the signature scheme. Technically, it's Winternets-based XMSS. So XMSS means that you have a Merkle tree of Winternets leaves, and your root of the tree, the root of the pub keys, will be your master pub key, and that doesn't change over the lifetime of the validator, and that can be used as a unique identifier for your validator.
Okay. And it follows the regular, format as any other validator address as of today that's used in Beacon chain. Is that correct, Justin?
Yeah, I mean, it's a slightly different format. It's a different number of bytes. So because it's a hash, it's maybe 32 bytes. Right now, the BLS pub key, I believe, is 96 bytes. So it's actually a shorter pub key. But this is just minor detail.
But yeah, so I'm still around. I had some connectivity issues, but isn't there a lifetime for this public key? Because you need to generate the Merkle tree, and then you have like the root, but this is only valid for so many like signatures, right? At some point you have to regenerate the whole tree again, and then you have a different public key.
Yeah, that's exactly right. So there's this notion of a maximum lifetime, and that might be on the order of a century. And then it's up to every validator to generate the number of keys that they want up to this lifetime. So let's say that you expect to stake for 20 years, you generate 20 years of pub key. That might take, I don't know, an hour of compute. And then you'll be set for 20 years. And if for whatever reason you want to do 21 years, well, you're going to have to be forced effectively to exit as a validator and re-enter with a new pub key. But hopefully, well, first of all, generating a very long lifetime should be fairly easy, but also the process of exiting and re-entering should also be easy in the worst case.
Thanks, Justin.
Yeah, and I also want to add that so I mentioned that if you are not, let's say like if you're okay here, so per block, right, this the slot is definitely going to change. The validators, it really depends whether there's like a new validator add or remove, but it also doesn't mean that when a validator gets added or gets removed, then the entire hash tree has to be recalculated, right? Because if we go back into this, let's say like this is the validator tree. If you're adding a new validator, then it might be the case that only one of the slot here is updated, and then it remerkalizes back. So only the hash tree that belongs to, say, the rightmost tree here gets rehashed, but the entirety of the left part of the tree doesn't get changed at all. So there's also like still a lot of like reduction of the merkalization that we need to do still, even for like a specific addition of like validator here.
And one small note, is that I expect all of the production grade merkalization libraries to do that optimization where they only remerkalize a small part of the state. So I'm actually a little surprised that it's only Grandine that has support for this. Like, my assumption is that all of them will have support for this. I mean, of course, there's the initial load, which we shouldn't be doing. We should only be loading the Merkle root. But then, well, I guess there's two things. Like there's the host machine that can load the whole state. And then really the only thing you want to prove is the diff. And for that, you only load in the zkVM the Merkle path that you're diffing.
Cool. Any other
questions for now? Sorry, yeah.
So can I ask, like, so the idea is like we would calculate the state transition before executing the zkVM and then pass it to it only the state changes to the guest in the zkVM, right? Like that's the way to
Yes,
avoid.
exactly.
Uh, so Justin, actually, I have a question on that because let's say if you're only processing, say let's say like a new validator is activating, right? And then you're like checking all the balance requirements and all the activation time inside the host machine, and the only thing you update is actually adding the validator to the state, and that's done inside the zkVM. Then actually the zkVM is not actually doing any checks at all that the validator is actually like according to all requirements, right? Then we are actually trusting the host machine that it's actually doing the all the requirement checks for the validators. Then it's basically just hashing.
No, so there should be no trust. So every action that's done by within the zkVM needs to be authenticated. So let's say that in order to activate a new validator, you need to check that they have 32 ETH. That's one of the requirements. Well, in order to do that, you need to load the balance. In order to load the balance, you need to provide the Merkle path from the balance to the root, and you need to verify it. And all of that you would do within the zkVM. And then you need to flip a bit, basically saying, hey, I'm active now. And for that, you need to do the same thing. You need to basically load the Merkle path from the activation bit to the root, flip it, and then re-Merkleize. And now you've advanced your Merkle root.
So do we need validation and computation on zkVM also? Is it right?
Yeah, so you need to do all of the state reads and writes, but only the relevant like partial paths. And then any logic, like a comparison, for example, you need to compare the red balance versus 32 ETH and check that it's indeed greater than 32 ETH. And that would be done in the zkVM. But ultimately, what you're doing in the zkVM should be minimal and extremely fast, especially once we have a snark-friendly hash function.
And trying to think quickly, like, does it make sense to say that if, like, for example, like state, any kind of like invalidation, any assertion that fails, that could actually happen outside the zkVM, right? But then only say the happy path that, oh, this block is correct, we could proceed to state that once like all those validation passed, then that gets sent into the zkVM, and then it does all its processing. But maybe that's doing stuff twice.
Yeah, so you're right. Like in the happy path, you'd be doing two things. You'd first have the host machine do it in plain text very, very cheaply. And then if it's all good, then you do the authenticated cryptographic stuff within the zkVM. There is one kind of design question, which is, do we want to have delayed state roots for the beam chain, similar to what we want to do for the EVM? Because if that's the case, then even in the unhappy path, we still want to have a notion of state root or some sort of a proof that some exception was hit. But that's fine. Like if there's an exception that's hit, then the host will pass to the zkVM all of the Merkle paths to prove that an exception was hit, and then we move on.
Any other questions for Anand? Cool. Thanks. Thank you, Anand. Can we then move on to the next? Are we just discussing what each person has been doing, or is there any other topic we'd like to have a chat about? Okay, if it's just status update, I can go. I've been going through the work that June and Anavit has done on just trying to understand how things are working, and that's what led me to a few questions on the partial SSD spec that we were discussing the other day on Telegram. Still going through the code, and that's what I've been doing for the past week.
Okay, I can do next. Thanks to Hayden, Baron, and Colby, we are implementing the STFs, and I'm reviewing the PRs, and hopefully we are ready to go to the make state transition on the zkVM for the whole epoch life cycle. So yeah, it's very thanks to everyone. And also this week I added the new integration of BLS backend, which is from the ZK crypto, and it is written in 100% Rust, and also SP1 supports the precompiles for its library. So I think integration can help our POC a lot. So yeah, we could use that one. So I did, yeah, those two things. One thing is BLS, and other thing is reviewing and fixing some consensus issues on the current implementation.
I can go next. So this week I implemented the I've been working towards the here, just one sec, I gotta fix my mic here.
I think it's working fine.
We can hear you.
Oh, okay. Oh yeah, so I've been working towards the process execution function, consensus function. I ended up implementing quite a few JSON RPC calls working towards this, and I ended up implementing the is valid block hash functions. I'm currently working on the notify new payload function in the denev spec that is required for the process execution function. And I've kind of just been chipping away at all the sub issues, trying to complete that one currently. Sorry, I didn't get as much sleep as I would like, so. And I guess that is my update. I'm just gonna keep chipping away at these issues I'm assigned to, and try to get as much done as possible this week and going forward. So.
Maybe I can go next. So past week, I think I spent probably like a bit less than half time on this, so not much of progress. But what I've done First is I try to add the Pico CKVM into the CKVM benchmark that's done by Succinct Residency. No blockers, not really, but it just takes time, like to like for each of the benchmark to prove itself. So it just takes time. The other thing, like I mentioned, the partial state writes, rewrites, and SSC partials. So yeah, so next week I'll continue to do the adding the Pico CKVM benchmark and also try to now like kind of tackle the CK STF and especially with like SSC partials, and partial localization in mind. I do actually have some discussion questions. First is on the benchmarking. Once like if we are getting back into benchmarks, I think one thing that we can do for sure is that we have all the state transition functions ready now, right? And then we have the SSE data, so basically test data from the consensus specs. So I think we can do all the benchmark against the consensus test data for sure. I think that's one thing. Another thing I want to kind of like entertain, maybe after we are done with that, is that maybe would it be a good idea to do something like ETH proof, but instead of for the EL layer, but we do it for the CL layer. The only concern I have is that I'm not so sure, like judging from the performance that I've seen so far, it's gonna take really long, or unless I'm missing something. I'm not so sure like we could even fit it like one slot per hour or something like that. So I'm not so sure if we are interested in that. I think we need to kind of like somehow scope down the state transition functions and only do a couple of ones that are like that we think is important. I don't have in mind yet, but maybe I don't know, like Jun, Varun, Kobe, Kaden, from your like experience with the state transition function, you might have some suggestions on like which one is important to have. So I guess that could be for discussion after the updates.
I think the last idea you suggest is super meaningful. The it's proof, the CL version of ES proof, and I think the current beacon state is like flat memory, so we have a lot of time and time consuming with serializing and deserializing the states. So it takes a long time. It's very obvious. So I think yeah, it's meaningful, and also the first idea you suggest is that we could also try the POC for our the current operations or state transition functions of the consensus backtest with our ZKVM implementation, like we did the process block header about a week ago. So yeah, I think we are ready to go for especially for the operations in the process block. So yeah, I could manage that.
I guess I'll give a quick update. So last week, I fixed a bug in our compute shuffled index implementation. I've also been doing most of the reviews for the PRs made by like Hayden and Varun and June in like the last week alongside June. And then I've also been putting more time into working on the like the peer-to-peer layer, like the request response domain. So hopefully I have something more to show in like a bit, and that would be nice. And then we could like run something live on the network. That'd be cool. But yeah, that's my update.
Yeah, short update from my side. I've mostly been reviewing a few PRs here and there, and I implemented the process participation flag updates function. But yeah, that's short update from my side.
Anybody else? Any updates? Right. I had just one question for Justin. Have the invites for the next Beam call been sent out? I asked because I haven't received one yet.
Thank you for the reminder. I will get it done today. Thank you for the reminder.
All right, awesome. Thank you. So if nobody has any other questions, then yeah, I think we can call it today. Thanks, everyone. And as usual, Anand, you'll raise an issue to discuss the agenda for the next call, right? On GitHub, and we'll take it from there. Cheers.
Sorry,
Thank you.
sorry.
Sorry, go on.
Especially.
So
Oh,
Kaden,
Thank you.
okay. I was thinking if I could join him on his tags on the core functions, the state transition functions.
Sorry, we didn't catch your
Am I
question.
audible?
Can you repeat it, please?
Hello?
Yeah, we can hear you. Please go ahead.
Okay, I was saying, I don't know if I can join Kaden on the call, on his stats on state transition functions.
So, did anyone
maybe-
catch that?
I can.
I think
try that.
I can answer this. So Mercy, I believe most of the state transition functions are almost done being implemented. Currently, there's a lot of work we can do in terms of testing. We have a lot of work in terms of like our peer-to-peer layer and integrating that with the core types we just implemented. Refactoring our code so we can handle testnets, stuff like that. I think in maybe like a week or two, we should have like most of the state transition functions pretty much done. But we're going to need to refactor them a bit to make them like usable for like actually running a node, for example. But that will probably take precedence as we need to do it. So yeah. I hope that helps.
I believe Kai Chen had a question as well. He raised his hand a while back. You can go for it. Are you able to hear us, Kai? Okay. Anybody else? Any last questions? Okay. Thank you then. Cheers. Have a nice day, everyone. See ya.
You guys have a good day.
Bye. Thank you.
Thank you. Bye.
Right.